Okay, so we're going to transition here from looking at situations where you were given the free body diagram, where you were told exactly what forces were acting on an object, and move into situations where you're going to have to identify the forces based off of what you know about those forces and what you know about the situation. So the first thing we're going to do is just look at basically the forces that we're going to go through. This is going to be a little preview of the next week or two, and then we're going to start going through them one by one and looking at what the forces are, when they exist, if there's any way of calculating them, some of them have a formula, and things like that. So here's your list of forces that we have. We have pushes and pulls, tension, gravity, the normal force, friction, and spring forces. Those are going to be the forces that we're really going to look at in depth. You see the symbols here. That's what I typically use. I always do F for force, and then sub P, sub T, sub whatever, to indicate what kind of force it is. You can use any symbols you want. It really doesn't matter. It's simply a variable, but that's what you'll see me doing. And you'll see some of them have equations, some of them have a few notes. Like I said, we're going to go through each one of these one by one, but this is a nice summary, something that maybe as you're preparing for the test, you might come and look back at. All right, the first force we have really is just a generic force. I just call those pushes and pulls. A lot of times in the problem, there'll be some object pushing or pulling another object. And I'm just going to call that FP, the force of the push or the force of the pull. All right, nothing fancy about that. The other one that you're going to see a lot that's also relatively basic is the tension force. Okay, so tension is a force from any rope or a string. All right, we call that a tension force, and I usually abbreviate that as FT. So we have FP for pushes and pulls, FT for tension. One thing to keep in mind, and I know it sounds silly when I say it now, but it probably will come up at some point, is that tension can only pull. Okay, so if you have an object here and there's a rope like that, that rope can only pull on the object. It can't push the object. If you ever try to push an object with a rope, it doesn't work out so well. So tensions can only pull. Like I said, it sounds silly now, but it is something to keep in mind because it will come up at some point later. The next force that we have is gravity. This is the force that we've been calling the force of Earth for all this time. Most of you knew that the proper name was gravity, but now we're going to start calling it by its proper name, which is the force of gravity. Here's what we know about gravity. The first thing that's important is it acts on all objects on or near the surface of the Earth that have a mass, and it always points down. I always say that gravity is the easy force because we know it's basically always going to be there unless we have a problem in outer space. We're going to have that force of gravity acting down. That's one when you're drawing your free body diagrams, right off the bat you can say, oh, there's Fg acting down. Gravity also has an equation that we can use to find it. All right, so the force of gravity can be found with this equation here, Fg equals mg. So that's how we're going to solve for the force of gravity. The force of gravity is going to be the mass of the object, okay, given in kilograms, that's our standard unit for mass, times g, our acceleration due to gravity, 9.8 meters per second squared. Notice this value for g is a positive 9.8 meters per second squared because g itself is a positive number. We oftentimes will make this force negative because it's going down, just like we oftentimes made the acceleration due to gravity be negative because it was going down. But g itself, that quantity, is a positive 9.8 meters per second squared. The reason why I tell you this is I want to make sure that you don't double count that sign and say the force is negative and also say that g is negative, and then you're really accounting for the fact that it's going down twice. G itself is a positive number. Now that we've introduced this idea of the force of gravity, we need to talk about a very important distinction that I haven't made a big deal about up until this point, but I will start now. And that is the distinction between weight and mass. These are two different quantities, even though they're often used interchangeably. So the biggest difference is weight is a force. So weight is the force of gravity. Okay, we can say weight equals Fg. Those are two synonymous terms. All right, it's measured in newtons since it's a force. Okay, and weight actually changes depending on the strength of gravity. That's a big distinguishing characteristic between weight and mass as well. All right, if you go to another planet, the moon, Jupiter, whatever, your weight will change. The force of gravity acting on you will change because G, that 9.8 on Earth, that number will change. Mass, on the other hand, okay, is not a force. It's really a measure of the amount of stuff that you have. I know that's really not the best English there, but that's what mass is. It's really a measure of the amount of matter contained within an object, the number of protons and neutrons. Okay, the standard unit is kilograms, right? Although there are others, obviously grams, etc. And mass does not change with the strength of gravity. So if an object goes to the moon, its mass remains the same. All right, and that really comes from the fact that mass is the measure of the amount of matter. The amount of matter contained within an object doesn't change when we take it to another planet. How much gravity pulls on that matter, the force may change, but the amount of matter itself does not. So the mass stays the same, but the force or the weight may change. Down here we have, and we've been doing this throughout the year, important things to know. All right, and this really is just a summary of this table, that mass and weight are not the same, and the key difference is that weight is the force of gravity, whereas mass is a measurement of the amount of matter. One last thing that I always find interesting, in the US, when we put ourselves on a scale, all right, we weigh ourselves, and we truly do weigh ourselves because we get our weight in pounds, okay? Now that's not the standard unit we've been using for force. We've been doing newtons, which is what weight or the force of gravity normally will be in, but pounds is another unit, all right? If you go over to Europe or most foreign countries, what we have is when you stand on a scale, you actually get your mass in kilograms. All right? So the two different countries, not only do they have different units, but they're actually technically measuring different quantities. This leads us into a conversation, another important conversation to have, which is how does the scale actually work, and would it correctly measure mass on the moon? So let's think for a second. What is the scale actually measuring? If we have a person standing on a scale, the forces we have acting on that person are gravity and the force from the scale pushing up on the person. So what force does the scale actually measure? It actually measures this force, the force that the scale pushes up on the person with. And the way it does that is because when the scale pushes up on the person pushes down on the scale, and that's what the scale is truly reading, but that force is equal to the force that the scale exerts up on the person due to Newton's third law. Okay, so that's what the scale is truly measuring. Now, how do we get our weight from it? Well, if our acceleration is 0, that means that the force of gravity simply equals the force of the scale, and we get a correct reading. Now, if the scale is measuring force, what we do is we take that force of gravity and we use it to find the mass. We know that Fg equals mg, okay? And we can actually calculate the mass. So just to recap real quick, because this was a little bit confusing here. When you step on a scale, the scale directly measures the force between you and the scale, that third law pair. Since there's no acceleration for you if you're just standing there, whatever force that scale exerts up on you is equal to the force of gravity. And if we know the force of gravity, we can calculate our mass using Fg equals mg. Okay? That means that on the moon, okay, a scale actually is not going to work to correctly measure mass because scales on Earth are calibrated for a G value of 9.8. Right? They're set up to calculate that mass based off of G being 9.8. If we go to a different planet where G is no longer 9.8, okay, we can't accurately measure our mass. This leads us into the idea of inertial versus gravitational mass. There's actually two ways of measuring mass. The one you're most familiar with is the gravitational mass, and that's what we just talked about with the scale. Gravitational mass is a passive measurement, so the object's at rest, like standing on a scale, and it uses the gravitational force. Okay, so when we are standing on a scale, gravity pulls down on us. We measure the force pulling back up and use that to get the mass, to calculate the mass of the object. There is another way of getting mass, though, and that is with inertial mass. Okay, so inertial mass happens when we have a dynamic or moving measurement that does not require gravity. So an example of this would be if we have an object and we pull on that object and measure the force that we pull on that object with. If we knew that force and we knew the acceleration, okay, we could simply use F equals ma to calculate the mass of the object based off of the force we pull it with and the resulting acceleration. So that would be a way of determining the mass of an object using the idea of inertial mass. It should be noted that these two are the same, okay? Inertial mass and gravitational mass, they're not different quantities. Right? The mass of an object is the mass of an object. The only thing that differs is how we go about measuring that mass. That's really what this difference is. It's a nitpicky thing, it's a little thing, but it is something that we do need to mention and briefly talk about. So just a few quick questions here about this idea of gravitational versus inertial mass. The first one we already answered. Does the mass change depending on how it's measured? No, mass is mass. These really are just about the method we use to measure it, and they don't affect the final result. What type of measurement is it when you step on a scale? That is a gravitational mass. And lastly, how could you measure the inertial mass? We also already talked about that briefly. Pulling a box with some force and measuring the acceleration. And then we're just using F equals ma to calculate the mass of the object based off of the force that we know and the acceleration that we know. The last specific force we're going to talk about for now is the normal force. So the normal force is the force from any surface, whether it's a wall, a table, the floor, a ramp, etc. Any surface that exerts a force, and oftentimes it's a supportive force, but not always. Any surface that exerts a force, that's a normal force. The reason why we call it normal, normal in this context does not mean normal as in the opposite of weird. It means perpendicular from a mathematical standpoint. When we have a line that is normal to another line, it is perpendicular, and that's what's going to happen with our normal force. It's always going to be perpendicular to our surface. So if our surface is horizontal, our normal force points up. If we're talking about a wall, our normal force points out from the wall. If we're talking about a ramp, our normal force points perpendicular up at an angle. So it's always going to be perpendicular. We abbreviate it just as Fn, okay, for the normal force. Sometimes you will hear it referred to as the apparent weight of an object. The reason for that is this. I always imagine being in an elevator. When an elevator is accelerating up, you oftentimes feel heavier than you actually are. The reason for this is not that your force of gravity has actually changed. That most definitely has not changed when you start accelerating in an elevator. But what has changed is the normal force the floor exerts up on you has increased, allowing you to accelerate up. And so you feel heavier, you feel like you weigh more, which is why normal force is referred to as your apparent weight, because that's really what you feel, right? The weight that you feel is actually the normal force, not the force of gravity. So we're now going to work through a few practice problems with this. Here's the first one. A person is lowering a 10-kilogram bucket from a well with a rope. Bucket's accelerating downward at 1.5 meters per second squared, and we want to know the tension in the rope. So what we want to first do is draw our free body diagram. We have the force of tension going up on the object, okay, because the rope is above the bucket. We have the force of gravity going down. I always put the mass of the object inside the box there, 10 kilograms. And I'm always going to label the acceleration too, off to the side here. It's not a force, so I'm not going to put it all on my object like it's a force, but I am going to put it off to the side because it does matter and it does impact our problem knowing which way we're accelerating. So what is the tension in the rope? Once I have that, I'm going to set up my F equals ma. In this case, it's just in the y direction. You don't necessarily have to add the subscripts, but I do want to make sure you know I'm not leaving max out. We just don't have any x forces here. So I can say the sum of my forces in the y is going to be Ft minus Fg, and that's going to be equal to mass times my y acceleration. Two things I can do. I can start filling in equations for things that I have an equation for. So Ft minus force of gravity I know is mg, so I can make that substitution. And I'm going to fill in for the mass that I know. I know my mass is 10, and my acceleration is negative 1.5. The reason why it's negative is because we're going down. So I can say Ft here minus the mass of the object, 10 times 9.8, is equal to, this side becomes negative 15. I can go ahead and solve for my tension, and I find that my tension here is going to be 83 newtons. And so that's my final answer. Moving on to the final problem here, we don't actually have to do a numerical calculation for this one. We're just asked, a person is standing on an elevator, and we want to know if the normal force is greater than, less than, or equal to the person's weight in a few situations. So I'm going to start with the forces acting on the object. I have my normal force going up, and I have the force of gravity going down for this person standing in the elevator. So in case number one, my acceleration is 0, and we want to know, is the normal force less than, greater than, or equal to the force of gravity? And the answer is going to be equal. All right. The fact that we have no acceleration means those forces must balance. For situation B, the elevator is accelerating downwards at a rate of 1.5 meters per second. So in this situation, we now have a downward acceleration, and that means that Fn must be less than Fg, because we ultimately need a net force or an unbalanced force going down to lead to that downwards acceleration. Lastly, for part C, the elevator is traveling upwards at a constant speed of 3 meters per second. That once again ends up being a zero acceleration situation, which means that these forces are equal. Once again, we have no acceleration, just like in A, so the forces are balanced.